It is my pleasure to introduce today's speaker, Charlie Marcus from University of Washington, a high-flying guy. He has the Boeing professorship at that university. Charlie did his undergraduate here at Stanford, then graduate studies and also at Harvard, then came back here as an assistant professor. Came up the ranks, but decided that he wants to go back to the East Coast. So he spent 20 years at Harvard, built their facilities for some of the best facilities I've seen for doing high-level condensed matter physics. And while being on sabbatical in Copenhagen, the new boys, he noticed that something is very rotten in the kingdom of Denmark, and he decided that he's going to fix it. So he decided to stay there for a few more years. And while he was there, and the year was 2013, in fact, November of 2013, I was doing my usual few months in Paris that I've been doing for years. And Charlie was already in Copenhagen, and he noticed that the weather in Paris is nice, so he said, "Can I come? We need to talk." So he came, and these things you can see that's from my is it the pointer?
It could be a number.
Yeah, it is. Oh,
Yeah, it's ready.
yeah. So you can see that this is from November 20 of 2013 when he did it in Paris. This is the Caroli-deGennes-Matricon. I had an apartment a few meters away. It was a nice day. You can see his pictures there. When we started to talk about trying to get him to Stanford with the idea to start a new program here at Stanford in quantum physics. I mean, that's basically what he came to do in the Mesoscopic Physics. But I thought that it's time to do something at Stanford. The whole world at that time was gearing up in what nowadays people call the second quantum revolution. So as we talked, we started to put together a document that was submitted to the university higher ups. And that's one of the early, this is I couldn't find in my email anything before 2014, but we had earlier drafts from before that. But you can see that this one is from March 12, 2014. He sent me the current draft at that time. And you can see here that for the first time, we coined the name of this new entity institute that we wanted to put together at Stanford, and we called it QFARM. And here is some of the what we said about why and background, etc., etc. This followed with an offer that this guy got from us, or almost an offer such that at the last minute we couldn't compete with Microsoft. That said, well, if you stay at NBI, we'll give you X amount of money to do anything you want. So he decided to stay there, which did for so many years until he moved as a Microsoft and NBI employee. I think he moved about a year ago to the University of Washington as the Boeing professor. So Charlie is now on our course. He is well known for his work in quantum physics, quantum device physics. He was awarded the Olsen Gold Medal in Physics from the Society for the Dissemination of Natural Science in 2020, and the industry prize of the Danish Academy of Natural Sciences in 2019. He's a member of the National Academy of Science and a few other organizations. So I think it's time that I stop.
Thank you, Aaron. I think that it's a pleasure to be a Q farm. It's a pleasure when dreams come true and ideas work. I think that one needs to go further in this forum to get a sense. It's pretty amazing. It really is a success story. So congratulations to me and Aaron. Congratulations to everybody else who worked so hard to put together Q farm. And take something which, you know, nothing in the world is easier than writing a 5-page document. And but turning Q farm from a 5-page, you know, idea, you look at the text. Exciting opportunity. Well, it's not an exciting opportunity until you actually do something. So thank you, and thanks. It's a pleasure to be here and to see what success story looks like. Now I'm going to switch to give a talk.
I just gave it to
You gave it to you. It was a terrific one. I'll give a different talk. Different aspect ratio in the slides anyway. I'm giving 2 talks. I'm giving one today and one tomorrow. And the one tomorrow will be about Josephson junction arrays. And one today will be about topological states and how to control them in phase. So totally different subjects, materials, like you just heard. But this one's really about, it's related to the work that I was doing with Microsoft over the last decade. Now that I'm at the University of Washington and still at Niels Bohr Institute. That's a complicated story, but I'm still retaining that affiliation. That the Majorana work will change all the other things now about Microsoft continues its journey to produce a quantum computer based on ideas that are sort of extensions of what's in this talk, though my own personal interest is not in turning this into a computational tool, but rather just understanding the physics. The physics of Majorana is interesting, I think, because whereas we are used to the idea of bosons and fermions as fundamental particles in thermal classification of particles in 3 spatial dimensions, that in reduced dimension, other things can happen. Anyons. Work over the last decades in fractional Hall effect, Laughlin fractions, their relationship to billions, called billion anyons. And what I mean by that is the exchange statistics of particles can be a fraction, not necessarily 0 or a 1 or a minus. But there's an even more exotic possibility that can exist in 2 dimensions, which is encircling a particle with another particle of the same type would give an entirely different related wave function. That is, it needn't pick up just a phase, it would really be a different state. And if you want, you can say that this state is remembering the time history of where those particles came from. And maybe, maybe you can make this seem less exotic and surprising if you think of this as the weaving of fabric. The shirt that I'm wearing encodes the memory of every needle that went around every other needle that made the fabric tie itself in a knot. And as you can see, it's a pretty robust memory. That is, the geometry can change, but the topology stays the same. Exactly who went around who is encoded in the fabric. And there's, as I asked, is there a quantum mechanical version of that? And yes, there is, as long as you have some third dimension into which the memory can be encoded. So maybe it's less than a state. But to create particles that have this characteristic takes a little bit of a trick. And this talk is about one round. We were inspired by a paper from around 2000, 2001 from Alexei Tayev, who described a system. This theta constitutes a superconductor on which some one-dimensional crystal, one-dimensional wire could be laid out, and by proximity effect, if a superconductivity was induced in this one-dimensional system, then as you read from the abstract, this certain one-dimensional family systems can have an energy called spectrum of boundary states are described by one Majorana operator per boundary point. This Majorana operator is characteristic. This did not light up the world, the experimental world. I don't think that Alexei could have done a better job of hiding it, not only by publishing in this journal, which I don't even know what that stands for, but not even in that journal, but in supplement to that. And you know, the effective job. And then not only, but in the great tradition of physics of putting key pieces of information in the footnotes of papers, he even not only published it in here, but in the supplement to there, and then put maybe the key piece of information in a footnote, which I've dragged up. And it says it appears, so here, you know, here's where you get unexcited about it, which is that this theta indicates a not just any superconductor, but it has to be a P-wave superconductor. But then even at the throwaway last sentence of a footnote in a paper published in this obscure journal, he said, it appears that only a triplet P-wave superconductor with a three-dimensional substrate can effectively induce the desired pairing between electrons with the same spin. At least this is true in the absence of spin-orbit coupling, which is almost like saying you should use spin-orbit coupling. Almost a statement which constitutes the entire rest of the talk of how to make such a state. These particles, which shouldn't be thought of as particles, which they should be thought of as the delocalization of the density of states to be located at the boundary of a system. It could be two dimensional, or this is one dimension, in which this topological activity has been induced. So if you, through a mechanism which I'll spend much of the talk discussing, induce this topological superconducting state, then its signature will be at the boundaries of that system. In this case, the boundaries are the end of the wire. The boundaries of that system, there will be a state, and that state can either be occupied or unoccupied. And the interesting thing about it, this particular thing, is that that two-level system, which constitutes a qubit, if you want to speak in the language of quantum information, is undetectable by any local measurement at the end. That is, I can't look at this red ball at the end and find out whether or not the state of the combined wave function is occupied or unoccupied by an electron. But by bringing the two ends together, I can find out whether or not they fuse, as it's called, into either an electron or an unoccupied state. But I can't tell when they're separated. And so if you want to call that protected information, you can simply say that the wave function of the electron is delocalized to exist at two ends of the state, and that it lives at zero energy, meaning in the superconducting language, in the middle of the gap. A very seat of the pants, don't take it to the bank intuition for where this came from, if you want. And there's a lovely paper given off that describes this in great detail from 2001. You know that if you exchange the position of two electrons, that the overall wave function of this two-electron system will pick up a -1. That's the nature of the variable. Well, I just said that that the Majorana state is like a half an electron because the electron gets delocalized. One electron gets delocalized at the two ends of the wire. So you can think of my left hand, it's not an electron, my left hand is a half an electron. Partners over on the other hand. Which means that if I exchange this thing 2 times, then I get the same -1. Or The double exchange of those two is the same as wrapping one particle around another, and that's another way of getting that -1. So this is a exchange them twice. Swap them and swap them again. That brings this one all the way around back to the same. So all you get when you say you get another wave function, they're just -1s that emerge. But this is already an interesting, useful piece of information. This says that if I take two such Majoranas that are associated with a single electron, and I do a kind of move in which this pair of Majorana states, which are an electron or a vacuum state, undetermined, and I trade partners. Now I can ask, what about these two? If I fuse them together, do these two fuse to an electron or vacuum when those two did or didn't? So now think of it as initializing down here and moving and measuring up here. And these states will be different because they're now new partnership. The realization, and this is associated with not only Kitaev, but also Michael Friedman and Chet Nyack, was that this constitutes a means of computing. So even a few other measurement-based computing, gate-based gates are just these swap operations. How do you swap when you have a one-dimensional wire? Well, you have a branched wire, and part of it you go down the branch, here these exchange places, and you will effectively change the place of the two of them. Just like if two people walking down the aisle of an airplane, one needs to get back to row 22 and the other person is in row 10. Somebody has to step into the seat, let the person go by, and then step back. So as long as a one-dimensional system like the aisle of an airplane has branches off its side, it's easy to wrap past people as long as you can step on the side.
So you're saying we're performing computations on there?
Yes. As in that oh, but only in business. That's how it justifies.
Only on Boeing.
So what happened next, and again, it took another decade for it to happen, is that the ideas of Kitaev, in particular this one about the end of the footnote about spin-orbit coupling, was not only formalized and written down, but numbers were put in for real materials. Like, we have a dilution refrigerator, it only goes to 10 millikelvin. Okay? We have aluminum that has a gap of 1.5 Kelvin. You have indium arsenide, we were just talking about in the previous talk, so we know what spin-orbit coupling is. How does it work out? If you actually plug in those numbers, do you get something where it's hopeful that you could stick it in a real dilution refrigerator with real indium arsenide and real aluminum and actually get something that would be measurable? And that's what happened more or less at the same time in these couple of papers, and they studied the problem of a certain spin-orbit coupling, a certain applied magnetic field, and a certain superconducting gap, and found that in fact a topological phase of superconductivity exists. It exists in a place where you normally, you have a tiny bit of background in superconductivity, think that the condition for destroying superconductivity is met. Namely, if you apply a Zeeman field, which likes to polarize spins, that exceeds the superconducting gap, which likes to have an S-wave character, that you yank the spin like this and it says, forget it, I don't want a superconducting. However, in the presence of spin-orbit coupling, it's more complicated. What happens when the Zeeman energy exceeds the superconducting gap is, rather than destroying superconductivity, a new superconducting phase appears, and that new, with sufficient spin-orbit coupling, that superconducting phase will have this character that there will be, it's as if it inverted the gap without destroying superconductivity, and the endpoints will be these Majorana states, which really constitute a single zero energy state for an electron that can live with that state. So with that, I have to say the experimental community got pretty excited. This was like not so bad. I mean, the recipe was pretty clear. Like the recipe for Q-farm, there's still a lot of work to do. You write down the recipe, you still have a lot of work to do. The second thing, again, it was about the same era. This is from a paper from Chandra Sarma and Sinesky. About a year later, said, well, what do you look for? Like, there's not going to be a red ball. What's going to actually be the thing that shows up in the experiment? And the thing that shows up is, there's a density of states for an electron in the middle of the gap, which allows you to inject or detect a state and flow current through that state of single electron character, sitting right in the middle of the superconducting gap, but only at the ends of the wire. Naturally, in the middle of the wire, there is no density of states. Density of states do not propagate through the middle of the wire. It appears, and in a way, it's almost, you can see like teleported. This word has been used, teleported to the other end. In fact, you can see it yourself, except it's nothing magic. It's just that the wave functions delocalize part of the support here, and part of the support. Okay? So you inject one carriers, they pop out. Nothing. We talked about this a little bit already, which was this material that got invented courtesy of some efforts in Copenhagen. This was just about the time that I was visiting on sabbatical, that these materials of two principal players in the story, indium arsenide, which actually has this negative work function, and aluminum, which superconducts, could be grown epitaxially. And that epitaxial interface was the magic to allow rapid transition of superconductivity into the semiconductor. The semiconductor could still be depleted, it still behaved like a semiconductor, you could make a field effect transistor out of it, all the magic of semiconductors, only now it would proximatize very effectively and become effectively super. Our first round of experiments was 2016. This was following the 2012 work from Delft, which did not have access to these semiconductor materials they hadn't invented yet. And we use a wire that has the superconductor, two facets of this hexagonal cross-section nanowire, and found that it turned up the magnetic field at just about the magnetic field where you would expect the Zeeman energy to equal the superconducting gap. These two subgap states came down, met in the middle. If I compare that to what had already been predicted a couple of years earlier, 3 or 4 years earlier, theoretically, we started to feel pretty good about the fact that you had driven a state toward the origin, stuck at the origin. And, you might be tempted to declare victory at some point and say that was the thing you were looking for. But life is, as usual, more complicated than that. And a whole series of papers came out that are still continuing to come out. Here from Shankar Sarma's group and Steve Pan. A study of just how easy it is to get tricked, because lots of things will give those kinds of signatures. He coined the term in this particular paper of the good, the bad, and the ugly, representing different kinds of physical processes. So here's a good one. This is exactly what is supposed to happen. This is a clean wire proximatized by a superconductor, SM means semiconductor, superconductor proximity effect, and then all kinds of interesting, what if there's barrier, what if there's noise, what if there's noise in the G factor, what if there's noise in the gap, playing around with the numerics to find out what happens, and then asking the question, does this really look like the Majoranas that we want? So, because now it's a simulation, you can look inside, you can see what's actually happening. So at low magnetic fields, the wave functions are all over the place, but when you get to this magic number 1 or beyond it, you see, in fact, this delocalized state. This was for finite wire, so it should be one at one end, one at the other end, and it looks pretty good. The ground state are these two states, and it looks perfectly localized at the two ends. That's the good situation. If you go above Zeeman energy units, the gap equals 1, you'll find the zero energy state, much like the experiment, but there's other things that can happen. And you might say that doesn't look very similar to it's color. But for sure, by going up to these values, the wave functions are all over the place. They're really not localized in the system. And so one of the conclusions of this paper is you can't just find the zero bias business and say, we're done, we've got it. It looks just like, the logical arrow is going the wrong way. Theory says it should go like that and go like that. And so then it goes like that and goes like that. You can't say, there, I've done it. Maybe sometimes you can, but not here. Here, there's other things that look not so dissimilar. Now, in a kind of like arguably uncharitable next step, the theory paper went on to pull out data from various pieces of literature, including our own on the left. Thank you very much. And said, oh, we fine-tuned some. We said, in fact, we fine-tuned parameters. This is not my negative assessment of theoretical work. I'm just quoting that they say we fine-tune the parameters to fit. So they've got a lot of knobs in their numerics, and they were able to turn those knobs in such a direction that it looked kind of like our experiment. But again, the logic here really matters. Again, you can say, well, if I come up with a numerics that by fine-tuning I can show that it looks pretty much like what the experiment does. Does that mean something is or isn't or whatever? Generally speaking, what it means is that one has to be careful. One has to do other things besides this in order to lock in. Now, some people may say, well, why don't you just braid them and see if they braid and see if you get your -1? It's not even that easy, because then the theoretical papers, they came out and said, you know, there's situations in which even if they aren't Majoranas and you braid them, well, then the response could be, well, who cares? As long as I want to braid them. Well, that's what you would say if you're not a physicist, but you're an engineer trying to build a quantum computer. You say, who cares? Well, I care because I want to know what's actually inside of the system. So it's, again, it's just not enough to see certain features because it's a complicated system. Okay. Stop. Now I'm going to change the subject a little bit and we'll come back. So to review, the advent of the superconductor-semiconductor interface allowed a big motion toward this predicted red balls at the end of the wire with holding this separated. But the situation was more complicated because there were other things that were considered. That's what it comes. Now there's other ways, in fact, I'm being a little bit ahistorical here, that in fact some of these ideas were co-developing from 2000 parallel with the other ideas to talk about looking in the core of a vortex of a P-wave superconductor, or superconductor with spinless superconductivity. By spinless, no twofold degeneracy state, where the core of the vortex could also house a zero energy state. And if you want, you could say it's not so different because in fact it's a boundary of two-dimensional system. The boundary is a one-dimensional system talked about with ends. And we normally think of the boundary of a two-dimensional system being the rim. But if a vortex lives, inside the vortex is also a boundary of a two-dimensional system. And that boundary can also hold Majorana. So it's not so different conceptually. But it was a very different physical system. And so here, experimental detection of Majorana with the core of a magnetic vortex inside the topological insulator. This one happened to be telluride, selenide. But there was a whole literature that emerged in and around 2015 until basically now, looking at vortex cores in possible P-wave superconductors for these Majoranas in parallel development. I want to bring these two together in a geometry which is sort of like a vortex, but at the same time sort of like a nanowire. And that has those are wires in which the shell goes all the way around the outside. And this brings me back to a Stanford part of the story. William Little, who sold me my first car when I was an undergraduate, 1962 Rambler American. But in 1962 was a very good year. It was not only the year I was born, it was the year that Bill Little published with ARCS a means of detecting that the flux quantum in a superconductor had a 2 in the denominator, not a 1, meaning that it involved pairs of electrons, a single one. There had been some earlier experimental tests from Bill Fairbank also here, but this was an easy one. This simply said if you measure the critical temperatures of conductivity as a function of the applied magnetic field in a cylindrical shell superconductor, in which you could put flux through the core of the shell, that the critical temperature would oscillate, and the period of oscillation would be 1 in units of h/2e. And that 2, that magic 2 in the denominator, was the signature of Cooper pairing. And again, remember, the BCS was 57, so this was not very long after BCS, so pairing was not a slam dunk at that point. And this experiment fell along. This is experimental data of what happens when you put a magnetic field down the core of one of these nanowires with a superconducting shell, and it's an extreme form of the little Parks effect. That is, the superconducting transition temperature not only oscillates, but it goes all the way to zero. And so that if you go halfway in between half a flux quantum, there's no superconductivity at all. The superconductivity is completely destroyed. This phenomenon was called by DeGennes destructive superconductivity, destructive little parts effect, or destructive flux sensitivity. Because at a half a flux quantum, superconductivity is gone, and then it reappears, and then it reappears again. And if you look at this diagram, you can get a sense of what I mean by the superconducting phase evolving as you go around in a circle. So here it is evolving by 2 pi within this first lobe. Here it is evolving by 4 pi within the second lobe, minus 2 pi, minus 4 pi, as it evolves in each of these lobes, making this new low energy ground state. But if you're halfway in between, the critical currents that are used to generate the flux expulsion exceed the critical current of the superconductor itself, killing superconductivity. In fact, the mathematics of understanding this dates back also to the 1960s. I won't belabor this except to say that it's straight up mean field theory of across the Borkhoff with there's only one adjustable parameter in the whole thing, which is the critical temperature of the zero magnetic field. Zeroth lobe value is a number, aluminum, lead, niobium, or something. You have to put in some number that sets the overall scale, and everything else is determined. In fact, even this alpha, which is the parameter that controls superconductivity, is given by the diameter of the wire, the applied magnetic flux, the coherence length, which is in this case just dependent on the normal state resistance, and everything else is determined in here except this value of superconductivity. And what's remarkable is how well it works. If you plug this into the destructive regime, you see there's the theory curves, both for critical current and critical temperature, and there's the experiment curve, one adjustable parameter for the entire, all of those lobes. The one adjustable parameter is that number right there, that's the critical temperature or the critical current in forward and reverse directions is the one adjustable parameter. Everything falls out just from the geometry of the device and its normal state. It's just pretty remarkable agreement with the mean field theory device. Where life got more interesting, I want to emphasize that what I'm showing you here is just a shell. Now, we made a more complicated device, but I made it black and white for the moment. The black and white part is not part of this experiment. This is just a 4-wire measurement of the shell. See where the shell is superconducting or the shell is not superconducting. But now I'm making another part of the experiment, this part down here, because I want to find out what's in the core. I want to find out whether or not the core of a vortex of a two-wave superconductor has anything interesting for it. And what one sees is this. A little bit hard to see with the lights on, but I'll just describe it. There's a superconducting gap with nothing sub-gap in it. Maybe there, not much of anything, but basically a low conductance gap. In the zeroth lobe, where the property effect is effective and induces a gap inside of this core. But when you have one twist of the wave function going around 2 pi, you can say that the core doesn't exactly know how to get proximatized. It doesn't have a phase that it can pick up from the core. It winds by 2 pi. How does it solve the problem? It puts a vortex. The core has a vortex in it. And even if the wires bend, there'll be one vortex. It goes all the way through the whole thing. And in that vortex, lo and behold, the experimental data showed a number of subgap states, including one subgap state at 0 energy. The whole collection of subgap states is something which people in superconductivity know, and it's called Caroli-deGennes-Matricon states. Not a very mellifluous sounding name, but it means that the core of a vortex is a little bit like an atom. You know, you can imagine that there would be quantized modes inside of this circular object. Normally, in a metallic superconductor, those are extremely narrowly spaced. The spacing of those things is small compared to the overall gap by something like the gap of the Fermi energy of the metal. However, in the semiconductor, the Fermi energy and the gap are about the same order of magnitude. The nature of semiconductors, extremely low density states. So the gap, the Fermi energy is small. So these Caroli-deGennes-Matricon states are very readily visible. And all one cares about right now is whether they're even or oddly distributed. They're symmetric about 0 or symmetric about +1. So if you are interested and curious about this is now published now. But in these Caroli-deGennes-Matricon states are normally described in planar superconductors where the vortex goes through. And what we have is something like an analog of a Caroli-deGennes-Matricon state. It's not exactly a pancake. It's more like the states that live along the length of a cylinder. And instead of being discrete states, they're really Van Hoff singularities because it's extended in the third direction. But the states that live inside of this core have this character. And then what we ended up studying, so here's just an example of modeling how these Caroli-deGennes-Matricon states live. And it's interesting, you can see the flux dependence of the Caroli-deGennes-Matricon states. And again, roughly intuitively, you can say that the extremum of the lowest one, which is the farthest out in radius, is here in the middle at one flux quantum. But as you go to higher and higher Caroli-deGennes-Matricon states, you have to go to higher and higher flux to reach the extremum. Not surprising, because they're just in at a smaller radius. So they need more flux in order to penetrate and get to their maximum. So you can even do a kind of a location spectroscopy by seeing where the maximum are. But in any case, I don't think it's the key point. The key point is—
So the singular behavior at a half with jumping from no vortex to a vortex, that's why we—
Yes,
so you're seeing that.
no, that's exactly dead real. So this particular numerics was done for a regime in which there is not fully destructive superconductivity. It doesn't go all the way to zero and then back up again. It goes like that, but both experimentally and in the numerics, there's a discrete jump. And in the data, I skip one in the talk, sorry about that, but the data looks just like that. Non-hysteretic, but discontinuous. What's more interesting is finding out whether or not this object would have topological superconductivity in it. And that was a new calculation. This system hadn't existed before. This was neither a vortex, exactly, nor was it a wire with the Zeeman energy and all the stuff that Kitaev and Luchin or put on. It's a new system. This is a system surrounded by a wave function, a 2π twist in the wave function, and spin orbit coupling, and not necessarily any Zeeman. Different physical system. And so we didn't know, but when our theory colleagues plotted this invariant Q that characterizes whether the gap has been inverted and it has become a topological superconductor or not, there were regions, both in the chemical potential space and in the space of spin orbit coupling, in which, and in the rate of the wire, in which this quantity went negative, and the character of it being negative is that there's a topological state in this field. So, okay, after the fact, you can go back and you can say, oh yeah, actually, the zero energy state isn't unreasonable given the numbers in the spin orbit coupling. But it is important to say that there wasn't like a prediction that we were looking for. This was something that showed up in the lab and we said, what the heck is that? Big fat thing at zero energy. And it was after the fact, Sears went back and said, oh yeah, actually, this looks like it has all the key ingredients for a topological superconductor. Afterward, and even after that, we then said to ourselves, oh yeah, it's kind of like a vortex. I mean, the whole idea of the 2π evolution of the wave function around the shell being exactly what happens around a vortex somehow didn't dawn on us, maybe everybody else had figured it out, we didn't, had figured out that that's the analog of what happens when you put a flux through a superconducting shell, a la little flux. Okay, then you can really turn the crank on the numerics and really simulate the wire, band bending, gate depletion, all that stuff. And if you are in the regime in which there's topological superconductivity, like diameter by radius by spin coupling, et cetera, you pretty much get what you ought to. And it's interesting also to see, and this is experimental data, and it's true in the cylindrical case perfectly, that it's an odd number of twists of the wave function that you need. If the wave function evolves by 4π around the rim, then you get Caroli-deGennes-Matricon states, but not a state at zero. Only when you have 1 twist, or 3 twists, or 5 twists. Now, this is a hexagonal cross section, so it's not exactly the same cylindrical symmetry, it's not just that you have to frustrate the proximity effect. You have to frustrate it with the right parity of twists around the wave function to get this topological state. That's kind of cool. Zero energy states only in the odd nodes. And experimentally that was seen, but it was to me just interesting that it showed up through red balls. Now, I'm looking at the time, and I want to ask the host, am I supposed to end at a certain time? I see there's a clock up there, so I'm not worried about what time it is. I just
Before we,
for dinner. People start going out. No, do you want me to stop at 10? What? 5 minutes. 5 minutes before. Well, we have to work a little harder. I think that we're all sort of duly warned that no matter what you measure, even if it looks to your initial look like, oh man, we've got to be done now. You know, surely God could not conspire to make something that doesn't, you know, that's doing something that looks like that. But that's not the current state of play in this field. We work pretty hard. So the next thing that we did involved another aspect of superconductivity in nanoscale or femtoscale devices, and that's the Coulomb blockade, something that I think a lot of you might be familiar with. Let me quickly say that Coulomb blockade in superconducting devices was well studied. This is from 1990s semiconductor. Tinkham lab, other labs around the world. But I picked one, this happens that these authors you about what happens when you have a Coulomb island that's superconducting, straddled by non-superconducting reservoirs. In fact, this has a name in literature. That's an insulating barrier, and it's called an NISIN device. And you can have SISIS, NISIN, whatever. This one's NISIN device. And that's what I want to talk about. The ends supply normal electrons. The Coulomb blockade, controlled by a gate voltage, will allow these to go in when the energy of the N and N+1 states is degenerate, as we heard about in the last talk. But if the superconducting gap exceeds the charging energy, then that odd occupied state will be unavailable. And all that will happen is you'll go from 0 to 2 to 4 excess electrons. However, when that state is lowered in energy until it does cross, if I by one mechanism or another lower the superconducting gap, then I'll have a little region where the odd occupied state is available, and another little region where it's available, but mostly it's even, but a little step of odd occupied. And so finally, the system comes all the way down. The superconducting gap is gone. It can be a discrete or a continuous state, but there's no superconducting gap. And so finally, the odd occupied state is on equal footing with even occupied state. And then finally, you recover 1E Coulomb blockade. So 2E, then even odd, then 1E as the gap descends below the charging energy. So what happens when you make a wire that's a Coulomb island instead of a long one-dimensional wire? Well, it depends on how long it is. Let's start with a really little one. That's the smallest wire. It's an NISIN cylinder. And now we can thread magnetic field through the cylinder. And if we go to 0 magnetic field, 2E Coulomb blockade. You have to tilt your head sideways a little bit because this is now the gate that makes Coulomb blockade. So this is a Coulomb blockade peak, another Coulomb blockade peak, another Coulomb blockade peak, spaced by 2E. Then you all know that we can destroy superconductivity. There's an intermediate magnetic field where it's just a piece of metal, and that thing up there is just metal, NININ, we can call it. There, the Coulomb blockade peaks are exactly 1E spaced. Now the interesting part. What happens when we go back into the first mode? And what you can see is Coulomb blockade back. It comes back with 1E periodicity, but it's not equally spaced. They look like, you know, prison bars and prisoner escape. And it's that non-equal spacing when we look at even and odd spacings that I want to now pay attention to. It's also true in the second law, non-spacing. But this splitting of the spacing, showing that the odds are smaller than the evens every time, is something worth studying. Why? Because if I take two Majorana's at the end and I bring them together toward the ends of the wires, the energies that made those states degenerate when they were far apart will not be degenerate anymore. Now those split in energy. Is that what I'm measuring? The split in energy, the finite size gap that's responsible for these even odd spacing when there's a finite lift of the degenerate state? Let's find out. So in order to do that, we just made a whole bunch of different lengths, short, medium, longer. And in each case, 2e, then equal spacing for destructive, then prison bars. And the prison bars got smaller and smaller and smaller until you couldn't even see them anymore. Until all of a sudden, the even odd spacing was just gone. Now, if you were really careful and you really plotted out these school blockade peaks into hundreds of peaks, points over the peak, use some curve fitting to find where the positions were, really did this, really killed yourself, you'd still see that there was this remaining even odd character. Now, what's great about this particular experiment is it comes with its own control experiment. If you go to the destructive regime in the middle, N-I-N-I-N, and if you find even odd there, you're doing something wrong, because that's a metal island. And you can see that as you increase the number of spacings, this is what happens in the destructive regime at 0.05. And if you go in the first lobe, even the long wire has this non-zero even odd feature. So it's outside the error bars, it's measurable, although to your eye, those look kind of evenly spaced. But the computer knows. And you plot the energy scale after converting this spacing to energy using the lever arm of blockade peaks, and you find an exponential dependence. You don't find compatibility with the power law. You only find compatibility with exponential, although you could say, well, maybe it's actually changing power. You could tell some story. But if you wanted to find out whether or not this thing is better described by the exponential suppression of equilibrium or some Andrea bound state, as they call it, inside this wire, that would be the power law. That seems to be good. Okay. At some point, you can say, I can't think of anything else it could be. I think I'm personally at that point. Can't think of anything else it could be. I think that's the fairest way to say. Let's go on to other experiments then. So here's another one. This is a kind of an inside-out version of it. There's a superconductor, there's a quantum dot, and there's another superconductor. Now here, there were some predictions that were made about, well, about what wouldn't happen. You'll see that your logic is getting tapped in this talk. What happens if you measure something and something doesn't happen? And there's a theory paper that says if you do this, it shouldn't happen. Okay, and I get the question. I'm not sure where the answer is, but this is the situation. The paper said, and there's a couple others like it, that there's a famous reversal of phase to make a pi junction that occurs in the trivial phase, but does not occur if there are Majoranas in the wire. If there are Majoranas in the wire, there's a zero energy state, and you will not be able to make a pi junction by having an odd occupied state in the junction. I'm telling you, I'm really tapping your logic, because you have to think, if I do this and I don't see that, then I shouldn't have seen it. What does it mean? That's the game. So this says again, supercurrent reversals for an odd occupied quantum dot. So even occupied, it's another question. It's for odd occupied. For odd occupied quantum dot, the pi junction will exist in the trivial case when L and R leave superconductors, but not when there's a Majorana. Therefore, this is a great sentence. The lack of supercurrent sign reversal and also, I want to read the sentence above it. We also find that the mere consequence of Majoranas being, zero energy. Therefore, the lack of a superconducting sign reversal can also be caused by any trivial bound state. Doesn't need to be a Majorana. Anything that lives sub gap at zero energy would still be valid. Well, we have to measure pi junction, so we have to make an interferometer. So we take the same kinds of wires, and I've grayed out the gates that we're not using. This one is now a reference arm, so we can tune the conductivity. We have to come down here and go out there. So this is like a squid. But this one has a trapped charge in it. We can go through even and odd occupancy. This one doesn't. So now we have a dot in one arm, and nothing in the other arm except the ability to change the conductance. And the reason it looks so funny is because we have to make a squid where one part of it is made out of a straight wire, whose magnetic field you can put down the axis of the wire. So, you know, you have to bend the rest of the squid around the base. But that's what it is. Now, it is a little bit complicated, but let me try to walk you through maybe just the left side. In the zeroth low, there's at zero bias, there's a supercurrent. So that line all the way through is supercurrent running all the way through the squid. And it doesn't matter whether the quantum dot is an even state or an odd state or an even state. And that's for the case of zero magnetic field. If I go to the first low, where I think or I speculate that there are Majorana-Moses wire segments, something entirely different. Nothing, then a giant feature, then nothing. It's really not nothing. It's actually the same supercurrent that goes all the way through the system. This thing is so big and so dramatic that it swamps anything before it. So something is happening in the first low that's not happening in the zeroth low. Now let's turn it sideways. Zeroth low, first low. Zeroth low, first low. But now it's even quantum dots versus odd, even quantum dot versus odd quantum dot. In the even quantum dot, you see the gap, the destructive regime, the first low, and there's nothing here except that. In the odd case, nothing interesting. That is interesting. It's a Kondo feature. So again, the previous talk. But this thing goes all the way through the first low. And that's a good interferometer signal, but remember what we were looking for. We're looking for a pi phase. So again, we go to the zeroth low, where, remind you of the logic, trivial superconductors, pi phase shifts are allowed. They're not required, but they're allowed. And indeed, as you go from the even state, the odd state, to the even state, in the trivial case, zeroth low, you indeed find a pi phase shift. What about the first low? You can't see it, it's grayed out, but it's easier to see over there. We can measure the supercurrent. No pi phase shift. Now again, you prove anything, but it's a consistency check. Say you have a zero energy state, then you don't have a pi phase shift. If you have a trivial state only, you do. And again, if you want to see what a pi phase shift looks like, it's a maximum becomes a minimum state. Whereas the first low, a maximum stays a maximum. So, okay. Let's get one step more complicated, which is a dot. And now, if you let me introduce another letter, like T, call it T for topological. S was for superconductor, T is for topological. So now I'm going to be making a TITIT or an SISIS. I just put two barriers in the shell. Okay, and let's see what happens first experimentally. Experimentally, as I turn the magnetic field in the zeroth low, where I have SISIS, I have this gigantic superconducting state, 0 ohms all throughout. I find the destructive regime, I find a gap that reopens again, and I have some degree of superconductivity that remains. Okay, so far so good. I don't think anything shocking has happened yet. It's a superconductor, it just happens to be alleged topological superconductor. There's zero energy state. Well, we have a little more work to do. So let's look first at the S, and I'm going to call it a dot. There's a dot there. S, that's the wrong segment. SSS or TTT. In one case, 2E transport through the SSS case, and when I move to the first lobe, 1e activity. And you don't know. This could be for the experts in the room, zero gap superconductor. It's still superconductor, but you would have 1e transport. Okay, we have a little bit better. Let's now move to a voltage bias configuration and see what happens above the gap versus below the gap. Below the gap, the supercurrent peaks are at 2e spacing. Boom, 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 boom. Above the gap, they're at 1e spacing. Naturally, above the gap, single electrons propagate. Below the gap, they're propagating via some supercurrent state. But is it supercurrent state mediated by a Majorana, or is it a supercurrent state mediated by just good old superconductivity? A little bit more work. I realize I'm getting to the end of my talk. I apologize. In fact, I didn't get to the second half. So someday I can get good at playing. But let's look at what happens in this SISIS becomes TITIT situation. Again, 2e, now it's not full blockade, it's 2e supercurrent. Destructive, 1e supercurrent, then prison bar. Here's the peak value. You see at 0 how bright it is? The peak value is gigantic. Let's do some theory to try to figure out how bright that should be compared to there and compared to there. Here's the experimental data and the corresponding theory. This is the peak value in picoamps. As you go in the 0th lobe, then down to 0, then back up again. The black curve is experimental data. But what about theory? Well, there's two parts to this theory. There's the red dashed curve, which is just the supercurrent peak based on what the superconducting gap is. You barely see it. It's not what's going, not explaining this thing. But there's also the quasi-particle transport. It also doesn't explain that bump. What is that bump in? What is going on right there? Well, in order to study that with experimental data, and we have to include 3 different kinds of terms in order to understand why they went down, back up, back down again. Again, remind you what that looks like in the raw data. That's just that in the prison bars regime, it's not only that they're bent, it's that they get bright in the middle and then dark again. That's this bright in the middle and then dark again. But what is that? Well, the 3 terms now that you can include are, here's the quasi-particle from above the gap contribution. Strongest when the gap is small, like in the destructive regime. Here's the supercurrent from just the full gap. And here's this new thing associated with the subgap state. Here it happens to be 0 energy. There it is. Tune all of those things. You can't bump in the middle. There's the theory curve that gives you the bump in the middle, which tells you that on both the left, right, and center, there's a subgap state. Where is the subgap state located? Well, it's a little bit hard to tell. You could say that the subgap state here, the subgap state could either be in the dot, which makes sense, or it could be outside the dot. Either one of those would give these very bump curves, whether you put the left, right, outside, or the gap really in the middle. But whereas they both have a hump in the current, this one only has even odd spacing that matches. This is a theory curve that matches the experiment. Whereas this one will have a hump, but no prison bar bending. Prison bars will be straight. So I see what time it is. The second half of my talk is going to be about another way of controlling phase. For that, I needed a new material platform. I'll just tell you what the material platform is. I'm going to stop. The material platform is extending these nanowires where we can control phase by threading through flux into the 2-dimensional plane. That took another year or so after the original development of Krogstrup, Nygaard, and Jespersen, Copenhagen. And this was first done by Chris Palmstrom's group, Vod Shabani. Learned some lessons from Peter Krogstrup at the time, and it's now made an industry out of it. But it's a 2-dimensional platform, again, proximatizing aluminum and arsenide. And the new system, which I will not spend time talking about, is this Josephson junction made out of a superconductor, a wire bounded by superconductors, and spectroscopy along that wire. The theory, now a theory curve, a two-dimensional platform for Majoranas with bound states. Now, not bound by the edges of the wire, but bound by two nearby superconductors. It's a talk that we'll have to save for another day, but it's another way of controlling phase in order to allow the appearance of this Majorana state. With that, I'm going to stop. Thank you for your attention. It's hot in here. We probably don't want to watch. Thanks. Use up all the time. People should put apps. You have any questions?
All different
Okay. Sorry, we're out there. Be polite.
and they are all sleeping because of food.
Heat in the room. I think page 2 of the Q-form document has something about ventilation.
It's not right now.
Okay.